And mainly our focus today will be proving this van der Waerden's theorem. I assume some of you have heard about it, some of you not, and we will just informatively discuss some other results, but the main goal will be to prove this theorem, let's say, together with, we'll try to build up the intuition. And then we'll do some more exercises, and hopefully that will make the time. I try to do the time management well. Also, I encourage you to talk a lot, because because I exited the meet and I don't see anybody, so it would be good to talk. So let's begin. So let's just say what is the first main goal today is to prove this thing here. And it states that if we color integers in k colors, there's always an arbitrarily long arithmetic progression. Or in other words, we can take, say, look at the integers. And we assign them some colors, a finite number of colors. Let's say we assign them 3 colors and color them somehow. And this theorem tells us that in this case we have a 3-term arithmetic progression if we color the whole AP. And also this isn't limited to the 3-term. As I said, arbitrarily long means that we can have, this theorem will tell us that we have 5-term arithmetic progressions and stuff like that. Just to make it clear, is everyone familiar with what an arithmetic progression is? I mean like the normal one, so it looks rainbow, I'm sure.
Where is the 3-term AP?
Sorry?
Where is in this sequence? Where is the 3-term AP? Like 1, 3, 6.
Oh, there isn't one on this from 1 to 6. There isn't one. Yeah, good question. The theorem just states if we color the whole numbers, the a 1 will appear. So say this proves that coloring 6 numbers isn't enough. But if we were to try to do something like this, well, for 3 terms, even 10 won't suffice, but our theorem tells us that we are coloring the whole number line. So yeah, that's a good question, because this was a bad example. Our theorem tells us that we have to color them everything, but we will prove that bounds exist. But the first version is that okay.
And will there be a curling avoiding a 4-term AP?
There will I will put in a PDF of the Beamer once I get over it with the introduction.
So, like, is the subsequence of one color forms an AP, or what is it?
Yeah, a subsequence of one color. That's what we're looking for. So something that looks like this for the 3-term version. For example, this
the length of AP would be infinite, or would that be like limited?
If I heard the question correctly, you asked whether this theorem will hold for infinite term AP, right?
Yes, yes.
It won't, and that is actually our first exercise. I was just about to paste it. So before we get on to proving this theorem, which holds for finitely many colors and tells us about arbitrarily large APs, we are going to prove that we can't do that with infinitely many APs. So I will just insert something. Oh, the bad part about sharing everything.
I didn't get what you exactly said. Like, won't there be an infinitely long AP, or will the large APs can be finite? Like, there can be only one very large AP and
We
just
have no guarantee of an infinite AP. There won't be one. So just to make everything clear, take a look at the second exercise. It asks the question: is there an infinite 0-1 sequence? 0-1 sequence is just this, but instead of color, you can look at it as if a red-blue sequence. So we will just assign red or blue or 0 and 1. That's the same thing. Is there an infinite 0-1 sequence which contains an arbitrarily long arithmetic progression of zeros or ones, but does not contain an infinite arithmetic progression? So that's exactly a question. Does arbitrarily long AP imply that there will be an infinite one? So with that, this is the first problem, and I spoiled the answer. The answer is yes, there exists one. But I'll give you just some time to think about this question. And also, now's the right time to ask if the problem statement is clear. We're doing exercise 2.
Yeah, the problem statement looks good.
Come again?
Yeah, the problem statement is clear.
Yeah. Okay. If anyone has any questions, I can look at the arbitrary. Okay. If anybody is thinking about doing the first exercise, it isn't that related or important, but we just want to the answer. We just are asking ourselves if there's a subset A which has. If you take a set of all arithmetic progressions on natural numbers, A has to intersect every one of them, but not contain anyone fully. So we want to see if we can take, we can have some which kind of intersects every arithmetic progression, but doesn't have an arithmetic progression itself. Also, kind of a nice practice for construct count examples. This and for any infinite arithmetic progression, that's important. So I'll give just a few more minutes, and someone can speak up or write in the chat. Just some general tips. Do not overthink this one.
I think for this problem we can like every AP can be expressed as a pair A comma D, where A is the starting term and D is the common difference. A and D are positive integers, and since such all pairs A comma D are countable, so we are just done. For example, we can assign the number one a random color. Then we want to ensure that
You're talking about the first problem, right?
second.
Oh,
that
I didn't
we can
quite.
avoid an infinite sequence. Because every infinite AP can be represented as A comma D, with A the starting term and D the common difference. Like that's
Um,
basically n times n, and we know that thing is countable.
yeah, I get. So it's you will take like every term from an arithmetic progression, and because it is equivalent to n times n, you will just use that to take every one of them in some order, right? Did I get it?
Like one by one, I will just ensure that something, for example, first I color one randomly and then I color two by some other color two, in order to ensure that 1 comma 1 uh, like is not there, and then I go to 1 comma 2, like just random. I can just go randomly and one step by step ensure that a particular
Yeah,
AP doesn't.
and just it isn't clear to me. How do you avoid how do you ensure that there is no arithmetic progression within that your choices? I get how you're trying to pick a term from every arithmetic progression, but how do you avoid ending up with an arithmetic progression itself in A? And also for the example here, um, not sure if it works.
I
Not the
think
one I
that
had
works,
in
right?
mind. Yeah,
I think
okay.
that
I
works.
mean, yeah, but
Like
the
if
point
the
is,
skipping was, if it was skipping by n, then eventually you have n consecutive zeros or n consecutive ones.
yeah, that's true, but no infinite ones should be also true. But when I tried to construct it, I just took 2 to the k, not to think about bounding. But yeah, that's the idea for the second problem. Just go with ones and zeros. Um, just switch them and put more and more spaces between them, like 1, 2, 3, 3, 4. Okay. Uh, yeah. 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 You're right. So for did anyone can the person who gave the idea for the first problem speak again? I didn't understand how do you plan on avoiding having A also have an infinite arithmetic progression in itself, because I understood that you will just express all APs as like this, like A and D. And because this is countable, you would just take every a random term from this one, from all of these, because it's countable. But I don't understand how they plan on avoiding the. I mean, that's true, but I just want to see if I understood you correctly.
Yeah, actually, I found a flaw in that, so I will have to think again.
I mean, it's a good direction, definitely, because we want to have a term from this set, so that's true. Just okay.
I
Can
think
you
that
just
a
zoom in once on the exercise one once again?
I heard two people.
Can
Come
you just
again?
zoom in on the exercise one? Like,
Yeah, yeah, sure.
I think for the
So
exercise one, this idea of a comma d works because, for example, whenever we pick up particular a comma d, we just ensure that it has at least one common element with a and does not has all common elements with a. So basically, we will pick a particular term of that sequence, put it in set a, and we'll also pick another term of that sequence and throw it away and ensure it will never come back to set a. And throwing a particular term will not harm us a lot because a particular ap has arbitrarily large terms, so we can always pick and throw.
do you? I didn't hear everything of it. But just remember that the arithmetic that an AP is uniquely defined by these A and D. So I mean, you're there. Just you're you're also to select a one from each of these, but just to make sure there's no infinite arithmetic progression, you should think about the differences between them. Just make them sparse. Also, the keyword is sparse. Also, like here.
But we are one by one picking the APs and ensuring that will not come basically we can call a AP good if it has at least one element A and not all elements in A. So basically every time we are ensuring a particular AP would be good, and this process is fine because the thing which are we are working on is a countable thing. So I think this should be
Yeah,
fine.
but it shouldn't go randomly because I mean it is simple from there. But say you
we can
from
just pick the A plus dth
like
element. Huh?
it could be possible that you have chosen these things like this here a's to these, and what if you chose like these things by some some chance?
Uh, I
But
think I think his argument is actually fine, just because you
I
can
mean,
order the APs in some sense. Now, and now for each AP there are two possibilities, like they're through the ones or through the zeros. So again we can order these somehow. So
yeah, yes.
so and each AP we are including the starting term in the ordering, so we can just ensure that it eventually breaks and do it for each sequence inductively.
whenever we have a bijection, we can consider any random bijection from n to this set and do in that order. That if the bijection, like first look at f1, like if f is the bijection f1 f2 f3 and so on. Of course we can't go randomly like f1 f50, that thing. I think going randomly might
Yeah, I think there's some issue with the internet. Let me check.
Okay, something happened. um okay, Yeah. Just can someone confirm if they see the board again?
Yeah, it's visible.
Yeah. Okay. So, sorry guys for I have sometimes have trouble understanding other people's ideas by video. So if I got things correctly, the idea of someone's proof for exercise 1 is 1 or APs in some order because they're countable. And just to make sure everyone knows what are we talking about, like we have an n time, we have like grids, say, of A and Ds, and our APs are determined fully by these A and Ds. A is the starting term, and then A plus D, A plus 2D, and so on. And an AP is determined by these two things. And if we think of it as a grid, as I said, to see that it can be ordered in some line, just go in this twirly direction. So that's the first thing. And then choose one of each, but eliminate bad ones. So if you want to, I mean, this was not my idea about just choosing them randomly, but as I understood, you would only have like finitely many ones that don't work. So, and you have infinitely many each time you choose, so you would always find one. Or alternatively, instead of doing that, you can just choose a really large term. Meaning that if you were to say choose something from AD, say you ended up somewhere here and you chose this number n, and the first number you chose was say 1. For the next one, which would be, I don't know, 310.
Oh, what do you mean by ordering APs? Like, in what sense are you ordering them?
We're just ordering, finding a bijection to n in some random order. Nothing spectacular. We could go like by, say, sum A plus D equals n, and then prioritize A. That could work. So we can order them, say, like this.
Okay, got it.
Or yeah, and then for the sum 4 would be 1, 3, 2, 2, stuff like that. But that ordering doesn't matter. Just choose a really large one. So if this one was of size n, you would want the next one to be larger than 2 to the n. Just express the point. And then when you chose all of this, you won't have any arithmetic sequence because just the differences would be too large between any consecutive 2s. The differences would be always of like this.
I didn't get this large thing argument.
Yeah, if we want to choose our arithmetic sequences such that if we want to choose our numbers from A such there's no arithmetic sequence, say we want we've chosen some like 1, 2, 6, just to give an example.
So are you explaining the previous solution or telling a new one?
Yeah, I'm telling it as a new one. I mean, it's the same as the other one. Also, you go 1 times 1, choosing new numbers from APs. But instead of just eliminating, you would choose a rather large next one. So if you were to hypothetically say you've chosen 1 to 6, and these were also from some things, I don't know, A1, D1, A2, D2. And we want our next number to be of form something we're given, say AK plus D for some fixed A and D. We wouldn't want to choose some low number which satisfies this, like 10 or 8, because or like 3, because then we would have this thingies. And also we would have an arithmetic progression. We want to choose them really, really large, say larger than 2 to the 6, because if our sequence is really sparse, like looks like this, and the next one is just larger than 2 to the 32, and also satisfies the same form, we can always choose an arbitrarily large number, which is of our required AD that doesn't limit us. How would you end up with an arithmetic progression? You wouldn't, because the differences would be like, if you were to sum them, they would grow exponentially, and you wouldn't be able to have them equally. Is that clear?
I think along with 6, you should also do 7 and 8, so that every AP with the difference 3 like comes in them.
I'm not sure I followed what you said.
For example, the APA 9, 12, 15, where will it go?
Yeah, 9, 12, 15. We only, I hope I made it clear from the beginning. We're talking about infinite arithmetic progression. So if you
No, like
ask the
so
question
9,
about
12, 15, 18,
yeah.
so on.
Okay. This is actually, so the difference is 3. So this is 3k plus 6. That's the AD. So A is 6, D is 3. In our ordering, say like how we choose them. 1, 1, 2, 2, 1 by sum. So it will be somewhere around here where the sum is 9. So it will be like 8, 1, yada, yada, yada. It will be like the 20-ish something number we choose. So we would choose this first one to be, so it's just 1 plus 1. We would choose to be 1. Okay. So we are done with A and D sequence. Okay. And the next one, we want it to be, I mean, these are all kind of trivial, right? These are just, I mean, these ones with D equal 1, they don't make any sense because, yeah, we already took care of them. And the next one would have to be of form 2k plus 1, right? And we what I said is that we want it to be larger than 2 to the previous number. So we would go 2. And then we would come to the next number, which also this one doesn't make sense. So let's just put in 2. So it's 2k times plus 2. And we were like, okay, we can choose a 4 here, but we don't want to do that because we are really afraid of making our differences be large, because we want them to be sparse so we avoid any arithmetic progression. So I'm like, okay, I'll choose something larger than 2 to the this. I'll choose 6. And then I choose some really, really big numbers following our ordering of ADs and making sure the modulo is right. And then at some point, let's say the last number I had was something to this power, and I come to this point when I want to take care of the sequence 3k plus 6. I'll be like, okay, I'll just choose some a n minus 1 is here. I would just choose an to be of form 3k plus 6 and larger than 2 to the an minus 1. So in this way, and then I go further with taking care of the sequence 5, 4, or 4k plus 5. And I would also want that.
How did you get 2?
Sorry?
How did you get 2? Because 2k plus 1 doesn't have 2, right? And you are selecting that number should be in that AP.
How did I get this one? What are you?
No, how did you get 2 in the beginning? Like 1, 2, 6, right? So
Oh yeah,
did you get 2?
yeah. Two shouldn't be here. It should be something of form 2k plus 1, and that should be maybe 3. Okay, sorry, my mistake. Yeah, thanks. But the point is, in each step, we want our number to be in the right form and just to be larger than the 2 times the previous number, because then you can see that such sequence can't have any infinite arithmetic progression, because if the difference were d, then the difference between some consecutive ones is always at least there's a difference which would be at least 2 to the n minus n for some large n, and that would be greater than this d. Sorry if I'm not being clear with the scratchiness and everything. Is this exercise okay now?
I guess we can have a cleaner method also by that ordering property, right? That by just multiplying the position of that number in that AP with the given term, I think we can always generate a sequence such that all the numbers won't form an AP with the previous numbers, and then inductively this property will hold.
If I understood you correctly, you're talking about this thing, like the ordering doesn't really matter, like how we choose them just in some order. Yeah, I completely agree. It doesn't matter. I was just giving an example of this order, order this. The ordering, like doesn't matter. It can be random, totally. Just the only important thing that this is countable. And this is sort of a proof that it is countable. So
yes, so we can just bisect them to n as well, right? And then just then take that positioneth number of a given AP and select that. That will always be larger and by a difference greater than the d with previous number, so it won't form AP with that definitely.
Yeah. Okay. So to to just sum up this example I overly complicated, the main idea is just to choose one from each of these APs randomly in random order, and when we choose them, to make differences between them really, really large. So if we were to have an infinite sequence, a subsequence of difference d, that wouldn't work, because eventually the differences between consecutive things, I mean, if they're not consecutive, then the difference will be just larger, because as I said, you choose the numbers to be larger and larger. Difference is at least this, and this will go out arbitrarily larger than some d. So that's it. yeah, exercise 1 turned out to be pretty tediously explained for no reason. So if anyone just didn't manage catching this one, I assure you that you could like go over this thing again. It won't really matter for the next part. It was just sort of a short warm-up. And I'll just go ahead and delete this, and someone can maybe tell me if they tried solving the third exercise, the one which looks like the most fun problem ever.
Could you zoom
I
in a
mean,
bit? Could you zoom in a bit to the third exercise?
yeah, I mean, we are not gonna do the third exercise because it's, as you said, the least fun exercise on the world, but I just want everyone to take a glance at it. So the point is, if we have numbers from 1 to 9,
We are doing second.
no, we're not doing, I'm just explaining it
Okay.
because it's terrible. And we are giving them the two colors, then there is a 3-term AP.
Is it just a
And
case? Do we have to consider a lot of cases, or is there an elegant solution?
there is no nice solution that I know of. This was like the exercise for people who want to brute stuff, or maybe just discover some nice solution, because no, I don't know any nice solutions, but it can be helpful because this exercise might help you gain some intuition on how to prove the other thing is the general case, in a sense that when you will begin to like brute it, you would go like, okay, 1 is red, that is you can log that, and if 2 is red, then I know that 3 is blue, and just like that. But here you would, I think, have to differentiate cases. Just to get the hang of what do we want. We want to have something like this. How will we arrive at the proof eventually? We want to have a situation when we would have 2 red and a missing 7, which we know nothing about, and something else like 3 blue, 3 and 5 be blue, and also know nothing about 7, but because both of these like fake APs, the unfull ones, want 7, then we would know that 7 can be anything and we would be done. That's the like general idea of proving this, but you would only have to like brute it for a really, really long time, and you would get cases when you would have like these fake APs concurring at 9. So that is just a short story about the exercise that 9 is enough for 2 colors and 3-term APs. Okay, moving on. Now we're going to take 3 colors and prove the 3 case, and after that the general many colors and 3-term APs to see how will we move on to the final proof and its improvement. So
Is
I'll
it
just
true in general that you can replace 3 with n and 2 power n plus 1?
yeah. That's so. Say we call a number. So we had what we have, the number of colors was 2, and number of terms was 3. And this stated that the least that we need at least 9 numbers to know that we will have a 3-term AP. But this theorem says that we can do this for K colors and L terms. And now, so we want to find this function, or just to be frank, to prove that this number exists, this V of KL. And now our next point is to think about V 3, 3. So 3 colors, 3 terms, just try playing around with it, devise a general plan, just prove it exists. So do not try to find the minimal number. And I mean by do not that it misses the point of the proof, and it's very not fun to construct the counter example. Just any, and afterwards we will move on to 3 colors, K colors, 3 terms, and finally the last one. Does anyone understand what are we trying to do now?
Yeah.
Okay. Yeah, I forgot to say that monochromatic means single colored. That's terrible. And when I was talking about this, solving this 3-3 problem, what I meant by do not try to find the minimal number which works is that just try playing to see if you get any kind of intuition which will help us for the even more colors. thingy. Also, do not be afraid to use the fact that the exercise 3 that in a block of 9 we have, if we were to have 2 colors, we would know that there's a 3-term arithmetic progression.
I kind of had an idea. It's very loose at the moment, but I thought I'd just share
Yeah,
it.
yeah, I'm listening.
So we can use exercise 3. So we just consider blocks of 9, and we know that there has to be. Oh, okay. I'm not sure if this is correct. I don't think this works. But what I was thinking is
Yeah, I'm listening.
we'll single out a sort of color. Let's say we have red, blue, and green. We'll focus on green, and we'll say that there has to be at least one green color in every block of 9. And so we consider first 9, then second 9, and then third 9, and so on. And then we could probably use the pigeonhole principle and something like that to show that there has to be some kind of AP if we consider enough of these elements, because there are only so many possibilities of the position with respect to the 9. So the green could be the second element.
I understood your vague idea. So you would be like, okay, if I consider the blocks of 9,
Yeah.
I know that there's a green one, and also there, I mean, around, I mean, a bit less than this many options for the blocks. So you would say, okay, and I would just try to nitpick every green from this 9 one, and somehow pray that it turns out to be a 3-term AP. I mean, that's a good direction. It won't really work, but
Okay.
the general like idea of dividing stuff to small blocks and then thinking about them repeating is nice. But which fails here is because, like, okay, I know that I will at some point I will have some identical blocks. So now I'm drawing only blocks of 9. So and you would know maybe these 2, 3 are identical. So the green is on the same place. Say green is always there on the 7th place. I don't know. So that looks nice, but you can't really have much power over these things,
Right.
because you know where these lines are. But I like that idea, and think about that, and also think about classifying those fake, like thinking about the situation where you have like red, which misses something here, and blue on some other place, say blue, which also terminates to this one. So you know this one has to be green if you assume the opposite. So think about those kind of situations.
Okay. Okay.
Is everything okay?
Yeah, I don't know what happens. Sometimes I get disconnected and just reconnect again. I mean, my Wi-Fi seems to be working, like other things are working, but maybe because the Meet has many people. But is there? Okay. Yeah, I'm just reading this idea. I like the thing is that you focus on two pairs of numbers which have the same middle color missing. So am I right? So you're focusing. So you're another Indian guy just said if you have like situation like this, we want to think about this stuff, like the ones which have the same middle number. I mean, that's good, but instead of thinking about that situation, because like you don't really know when the middle number is gonna exist or not, it's just a drag. You could do the thing I said about, so like if you were to have blue like this, you wouldn't know and not know you have a missing one here, but for some other red one you could take, I don't know, it's to be, did I miscalculated, don't look at the dots, just assume that this is all equal. Yeah, we want to think about this.
Wait, I was wondering that if we had like some arbitrary n, let's say, there are 3 to the power of n possible colorings of that, let's say 1 to n, right? But could we count the number of colorings where these arithmetic progressions exist and show that for large enough n that is equal to 3 to the power of n?
Yeah, I see, but the main fault, like that will be idea for the other proof, like
I mean, even to prove that they exist, like for like showing that there is an n such that, you know, the two functions that like 3 to the power of n and let's say some other formula you get, that they actually are equal. Like, I mean, I'm not sure if this is possible. I feel like it would be very laborious, but okay.
It's gone again. Eeks. Really sorry about that, guys.
okay, let's do it together so we can move on. So we're resolving exercise 3 now. What was our thing? Okay. We are trying to brute it. So we know that the first one should be a red one because we can always block that. And if we were to have a red one, we can have it here. We would know that this one had to be blue. Okay, so this is, call it almost good block. we're solving exercise 3, so now we all again we have two colors. Almost good. So it goes like this. There are also some other almost good types. So we know the red one is the first. We could have a blue one here, then a red one here, and then we would skip this one and have this one blue. So this is also almost good, with the blue one being here. And there are also some other, like if we were to have this, we must have like a red at some point. So we would have two almost good things. And we can do the vice versa for blue. So in we could have solved the previous exercise by saying in a block of 6, so we're just counting this like expansion because you can go a bit further. You have an almost good pair. Is this clear? This is just we are solving the previous exercise.
Yeah, it sounds good.
Yeah, okay. And then we want to do the same thing somebody proposed. We want to look at our blocks of 6. And I'm asking how many different blocks of 6 are there? In 2 colors. We're just two coloring it. There are theoretically 2 to the 6 ones. Yeah. I mean, we're not thinking about if there's an arithmetic progression. So we know that there are 2 identical ones, right? And that the block of 6 must contain an almost good pair. So we know that there are blocks of 6. Okay. We're doing blocks of 6 because we're trying to look at the least size where you will have an almost good pair. And I mean, also maybe blocks of 5 could work. No, blocks of 6 because we want it to start with the red one. So I made a mistake here. So, oh, sorry. And you know nothing about this one. We're looking at the like what makes us fail. Like when you try to root this, you would be like, okay, if I have 2 reds, that I know I can calculate what would be the next blue one because it's a three-term arithmetic progression, right? So if you were to have 2 consecutive reds, then you know that the next one would have to be blue, and you can also try the same things. And just the claim is in a block of 6 you will have an almost good pair, and and we have proved this by brute. Also, it works same with the blue ones, but we just have to brute it again with the blue. So that's why the number is 6, but it doesn't really matter. What matters is that we want to use the same idea as we had, like somebody proposed it here, when we have identical blocks, but now we know that in this block we have an almost good pair, so that will help us. So take first 6 times 2 to the 6 plus 1 numbers. So as I said, we're getting worse and worse. So we have one almost good pair. which looks like this. It has something like this, and another one here.
Oh, what are these 6 times 2 to the power 6 plus 1 numbers?
These are, when we consider blocks of 6, there are 2 to the 6 possible blocks. So we want to take 2 to the 6 plus 1, so we can do pigeonhole and know that there are 2 identical blocks.
Okay.
Okay, so we know that we have some which look completely identical. There's also some stuff here we don't know about. And that they are almost good. And why does this help us? Because then we can calculate what is missing from them. And how do we do that? We can take the first red one from here and the second red one from here and just jump all over it to some number. But then, who can tell me if we take the blue ones, to which number will it lead to? Because yeah, like the difference here between 2 is some D, also some D, and then this is, doesn't matter, X. This is some D, D, and this is just calculated to make, to be 3D plus X, so it's like 2D plus X. And if you were to calculate this, like, because this is an almost good arithmetic progression, we know that RR and B are 1. So we know that the blue ones will also lead to the same number here. But we know that whether if it's red or blue, it doesn't matter, because then we will have an arithmetic progression. Is the proof of the previous exercise clear now?
I can't understand this last part. What did you do with the like circle after 2D plus X?
Yeah, I just said that if you have 2 blocks which are the same, and look at the almost good things in them. So I just draw something like this. There are many numbers between these two. We don't care about them. We just know that these 2 blocks are completely identical. And I just want to, I want to calculate what will be the terminating number of these 2 things. So I just, and I wanted to make, to prove that it will be the same one if you take the blue ones. And that is kind of clear, but I just wanted to like calculate it if this difference were D, this one is also D, and then this one is X, this one is D, this one is D. Then the difference between these 2 red ones would be 3D plus X. So you would go another X and 2D to this one. And you would say, okay, it can't be red, because then I would have this, so it must be blue. But then you would check these differences and see that, okay, from this blue to this blue, I have 2D plus X, but I also have 2D plus X here. Because this is the NAP, they're shifted, it will be the same.
Okay, I got it. But like, what did we prove after? Yeah, I got this step. So how are we done using this?
We are done with exercise 3 with 2 colors. We're done with this, because we have proved that there is an almost good pair in every 6 block. And then if we take just a large enough number, there will be identical 6 blocks, and then we could do this. And we can now prove the 3-3 thing by the same reasoning. We would say we would claim either there is a three-term AP or there are two almost good APs concurring at the same number. What this means is that we can take our proof of this to be our the thing we want, our inductive hypothesis, because we will be like, okay, now we can, because we've proved this, we can know that if we take three colors, we would have a situation of red, red something, and blue something, which will have to be green. So we want to, with the same reasoning as we did here, we want to find an almost good pair, which will be like which will be just the W of the previous function, and take enough of the almost good blocks so we could do the same argument. So here we have proved that V of 2, 3 is less than equal to 6 times 2 to the 6 plus 1. And in reality, we know it's 9, but it doesn't matter. What this means here is in VT32, there is an almost good pair. And by almost good in this new one, we mean like red, red, something, blue, blue concurring to the same thing. So we can do the same thing again. Does anyone see how do we proceed from this?
I have an idea. Sort of
Okay.
What we've kind of done is we've taken almost good pairs for 6 blocks, and we sort of zoomed out to consider blocks of the size 6 times 2 to the 6 plus 1. So what would happen if we zoomed out again? Because we've sort of forced there to be an almost good pair in in this big block. So
yeah, so we know that in this previous size of the block, so in our theorem here, we're just taking this and zooming out what you said. So I will call this number big N, the one in the previous number. If we take, we need to have like, because as you can see, this can exit a bit. This whole thing is N, and this will maybe be 2N, so, or something like that. Don't mind this. So we would say in 2N there's a good pair, just to make sure we are not out of bounds. So we would take then again some more blocks. And referring to the question in the chat, how many blocks do we need to have an identical block happening? We have three colors, I remind you. Yeah, so take 3 to the 2n plus 1 blocks. Why? Also responding to the question, because by pigeonhole there's a same block, identical. And we know that in a 2n we will have this situation by our previous statement. So let's just look at the same thing all over again. So what do we have here? We have like none, no, and also, and we know this one then has to be like green. And in the identical block, we have the absolutely same thing. I'm terrible with calc. This isn't an arithmetic progression. I hope that is clear, but we'll just pretend it is, like if you count the squares as differences. So can anyone tell me, I will look at the green ones and what is the missing one. But if I want to make sure that they this can't be red and can't be blue, how do I choose these ones? Can someone?
Right. So I think we take the first red point from from our first block, and the second red point from the second block, and then so we can force that can't be red, and then we see that the same thing for blue, and so it can't be red, blue, or green. So we've run out.
Yes, exactly.
I just kind of wanted to ask why we did 2n, because we can force an almost good block in n.
Yeah. I just wasn't sure about what the n was, if I'm taking the van der Waerden, the W of the previous one. So I was like,
Alright, so just
I'm moving things. I was like, first, like, is this? I thought I called this thing n. So I was like, okay, I'll just take 2n, not to think about the definition. But yeah, it should be n.
Right.
I was like, I was just thinking for a moment that I had some leftovers when I do this step, but yeah, I should have called just the whole thing n. So yeah, and as you can see, like this idea is essentially what we said in the beginning. Just the focus was to look at the faulty arithmetic progressions, and it really works because when we like how can we generalize this to a longer arithmetic progression? Like if we were to just look at it now, we wouldn't really know. Because, as I said, we would somehow need to make sure that all of these two n blocks, which we zoomed out, like if we were to look at the 4-term arithmetic progression, we would be just like lost here. Like we wouldn't know if we had another one which looked the same, but it isn't in a good place. All is done. So now actually is the time like to think about more colors. Is the thing that we need to know is that we need to induct, like say that, okay, we will color the new blocks in more colors and know that there will be a smaller arithmetic progression, like a 3-term one, so we can get the 4. So our next thing we want to do before we finish, and I apologize for taking too long. I was thinking about redoing the proof and a problem, but I will just try to at least explain the main idea of the proof, so we can so I can give out some problems and also what to read if anyone is interested, because there are a lot more things in this kind of Ramsey theory arithmetic progressions thingy. So I will be
I mean, I don't know in the general case, but for just three-term APs, we can simply continue on this process, and we can get this for any number of colors as long as we have three-term APs.
Yeah, so for 3 to
Yeah, this works immediately.
I maybe have switched the notation. I apologize for that. So this is terms. No, I think it was the other way around. So yeah, if we stay with 3-term AP, P's, but more colors, we see that we can basically just do the same thing. So now we know there's induct on number of colors. In V, K minus 1, free, there are K minus 1 almost good pairs concurring at the same thing. So we would do again, take blocks. And first more colors. So take first K to the V, K minus 1 plus 1. So and then the next bullet points. Oh, what am I doing? Okay. Yeah. Find the same block. And then we would look at its pairs like this. So we would know that we would have like Nana, these sparkly ones, doesn't really matter. No. And we would also do the same thing, take the first one here, second one here, first one, second one. These aren't at the same position, I'm just drawing them illustratively. And we would also take additional one, which I have it here. So with this, we are done with K colors 3 AP. We're done. But how do we move on to more longer APs?
Okay, so I kind of had a plan. I'm not sure if it's gonna work, but
yeah, okay.
So now that we're done with WK3, instead of going from here to directly to WKL for general L, we could start with WL. So like we keep the number of let the number of terms in the AP vary, but we use 3 colors only, so that we can get that initial block, like we can get the block size, and then we just do the same thing we did here. So if we can bound the initial block size for just 3 colors on any number of AP terms, and then we can just sort of do a PHP thing. I'm not sure if it's gonna work. It's just a suggestion.
Yeah, I see. I mean, I was thinking like our idea is generally like really nice, but the fact which makes it fail in arithmetic is because we would need, like, why does this fail? We would need to find the 3 of the same blocks. Yeah, 3 identical blocks we would want, so we can make a 4th one. I'm discussing the case where it's 4. Right. We don't know like how far these are.
Right,
but
right. So PHP, that's
we can use the theorem. We can use the theorem on blocks. Like we would say, okay, assign every block its color, and then apply the theorem with with more colors, but not as long arithmetic progressions. So we would get this situation. What I want to say is like, okay, let's try to discuss case when we have more keys, and I think that will make the general case more clear because, as I said, time is running up. So also consider they're almost good pairs. We know we have them inductively. So they would be of some size. I don't even care at this point, just in first n we know that there is a bound. So if we have an interval of n colored in 4 colors, we know that we would have this situation. So it would be like red, 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 something, blue, 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 something, and so on for every color. So we would have like A-1 colors, and this one would be the one which is sparkly. So how many different, and say this is of size n. So there are k to the n different blocks, right? And what would finish the problem if we had 3 blocks identical, which form an arithmetic progression?
Yeah.
And this is actually good because with that we have reduced this. Like we could assign every block a color because they're k to. We will assign k to the n colors, but we're using 3 long APs, so that's good because like we're double inducting, and first we're taking care of the length of the AP, so we know that is fine. Assign each block a color. So depending on what it looks like, just assign it a color, like doesn't really matter. And then color every block of n, starting from 1. What this means is that we can actually, like, if we were to take first n times v number of k to the n colors and 3 long arithmetic progressions, we know that there is a block which is an AP. So it would look like this. This would be identical. Oh, they aren't really identical. And we would know nothing about it. So we would again do the same thing, like look at all of its colors and take the first blue one, red one here, the second one here, the third one here, and the fourth one would concur, so we would be done. Because what we like, the only thing that makes us do induction here is the almost good pair argument, which is actually kind of nice because we would always have like this remaining thingy. Yellow one is the remaining one, which makes our pairs almost good, and then we would just go with this to add additional color, and then with that we have proved the theorem. So as I said, time is running out, so I have to wrap this up. Actually, you might wonder like how good are the bounds, and the bounds are just terrible. Like if you've noticed here, like what we did, like we're always taking some powers and powers. So all bounds are like tower functions. And the one we proved here is of form if they're, it's a K term, it would be of something asymptotically that looks like this, which is just unimaginable. So the bounds aren't really good, but the best one is also some tower function, which looks like 2 to the 2 to the 2 to the K. Not sure, something like that. And it has been proved recently. And another thing which I would encourage you to try finding out about on your own. Just a second. Oh! Oh my God. Is Shemered's theorem, which states that if you take that these colors are kind of equally distributed, I mean, like if you take a set, let's just read it. If you take a proportion of a set, like say a third, you can take this epsilon to be something less than 1, doesn't it matter? Like take any subset which is large enough, and it will have an arithmetic term progression for some n large enough. So like it's a lot stronger than van der Waerden, because van der Waerden states that we need to color everything, so the colors aren't really symmetric, but this theorem says that they actually are, and it's a lot harder to prove these kind of stuff. I remember I was on a lecture which we listened to the proof, but it was really hard for me to follow it. So you can try exploring that one on your own if you maybe know a bit more probability. Yeah, and also I will leave some more problems concerning this. There are 2 or 3 ones, which are just applications of this theorem, quite lighter than the proof itself. And yeah, I hope you really, I hope I got the time to answer some more questions, and that I wasn't all too boring today. And yes, thank you.
No, it was great. It was very nice.
Yeah, thank you guys. This was really fun. I'll try to figure out what happened with screen sharing, because the only window that wouldn't share for me was Microsoft Whiteboard. Maybe it's very bad.
Thanks a lot for coming. That was remarkable and thoroughly enjoyable. So yeah, thank you again for coming.
It was my pleasure. Yeah, and I will just send